Hi, I'm Jordan Bayton from LimitState, and today I'll be explaining how to set up and solve a grillage problem in Peregrine, the structural optimization plugin for Grasshopper. A grillage problem looks at calculating the optimum layout and width of non-prismatic beams in a floor system. Beam flange width is calculated based on the experienced bending moment at a given location, making the calculated beams more materially efficient than if prismatic sections were used. Grillage analysis can be looked at in isolation or as part of a whole structure, as shown later on in this video. In this simple example, I've created a square mesh which is going to act as the domain for the grillage problem. I've drawn 8 lines around the perimeter which define the location of columns supporting the grillage. For the loading, I'm going to use the distributed load component. The square mesh used for the grillage domain is used as the mesh input to the component, and a vector is used to describe the magnitude of the load. This is then connected to the load case component, which feeds into the problem specification component. Point supports have been applied to the base of the columns using the point support component. This connects to the supports component, which feeds into the design domain 1D component. This is used to set the design domain for the columns. The lines drawn in the geometry section feed into the line input. The material component has been used to define S275 steel, which feeds into the material input. The CHS cross-section component is used for non-grillage domains and connects into the cross-section input. The wall thickness of this can be controlled. The design domain is used to set up the grillage domain. The radio button should be used to select a grillage domain type rather than a truss. The 2D mesh defined in the geometry section is connected to the mesh input. The S275 steel defined in the material component is connected to the material input. In this example, nothing is required in the supports input as the load will be transferred to the columns. However, if no columns are present, support should be inputted here. The nodal divisions input defines the density of auto-generated nodes in the domain. The higher this number, the more accurate the solution, however, the longer it will take to solve. The I-beam cross-section component connects to the cross-section input for grillage problems. Sliders can be used to set the structural depth of the I-beams, the flange thickness to depth ratio, and the web to flange thickness ratio. I-beams of these properties are used throughout the grillage solution. Both the grillage domain and the column domain are connected into the problem specification component. The problem specification component connects into the layout optimization component, where the problem is solved. This is connected to the view solution component to display the result. As you can see in the solution, the midspan columns are much larger than the corner columns. This means that they are carrying more load and demonstrates that the midspan is a far more efficient location to place the column. The beams in the grillage have a varying flange thickness depending on the moment they are resisting. The largest beams are orientated so that they span from perpendicular center columns rather than across the whole building. This reduces their total span, which is one of the reasons why this is a more efficient layout. Grillage optimizations can be used in more complex and realistic problems, such as whole building layouts. This example shows a grillage optimization being used to design a whole building. The analysis in this example solves a grillage problem for the first 2 floors, a second grillage problem for the irregular shaped central tower, and sizes columns and lateral bracing. 2 load cases have been defined, one for the vertical loading and one for wind loading. Partial factors could be applied to the loads to create load combinations as load cases to match Eurocode guidance. Similar to the simple grillage problem shown earlier, supports are provided at the base of the lines used to define the columns. 4 domains are used within this problem. The columns use a 1D design domain, whereas the 2 grillages and the cross-bracing use the design domain component. The radio buttons have been used to select the type of domain. S355 steel has been defined in the material component, which feeds into all of the design domains. Similar to all optimizations solved in Peregrine, the design domains and load cases are connected into the problem specification component, which feeds into the layout optimization component. In this example, the outputted solution has a custom color assigned to it using the color picker component. This allows the output to look like steel. The solution shows a non-regular beam layout, similar to the one showed in the previous example. The beams have a varying cross-section depending on the applied moment. Midspan columns are larger than corner columns, meaning that they are in a more optimal location for columns to be. Grillage problems can be used for buildings of complex geometry and are a perfect design aid at the concept stage of a project. Thanks for watching. For more information, visit our website.